Hello, my name is Estella Weiss, and today I will be walking you through a problem involving a series of 3 gravity drain tanks. First, we will go through how to solve for the dynamical material balance, and then we will be using a proportional only controller to manipulate the inlets. Then I will show you how the tanks respond when we change the initial liquid level of the third tank and increase it by 20% from its steady state. Then we will finally look at the controller gain and see what its value is right before the system becomes unstable. So to start this problem, we can draw out our system. We have 3 tanks at different heights, and we have some different flow rates. First, we have Qn going into the first tank. We have Q1 going into the second tank, and then we have Q2 going into the third, and finally Q3 leaving the third tank. They all will have different heights, all different liquid levels. We can define them as H1 for tank 1, H2 for tank 2, and H3 for tank 3. Now, it's important that we also define the cross-sectional area of all tanks as A. They will be constant for all tanks, and they will all have the same cross-sectional area. They will also all have the same area of the outlet hole at the bottom, which we will define as AH. Now, the first step in solving for the dynamical material balance is we want to figure out what mass is in just this first one, just looking at the first one. So we can define that by getting its volume, which is the cross-sectional area times H1, the height of that liquid level, and then we can multiply that by the density of the liquid to get the total mass present in there. Now, the change of this total mass with respect to time is equal to what is flowing in, this Qn right here, minus what is flowing out, Q1. And these two flow rates will also be multiplied by the density. However, since they all have a consistent density, the density does not change with the liquid. It's all the same liquid. We can cancel out the density. So I'll just remove that there. And so this is what we have now. First, we have the injection work per unit mass, which is defined by P2 minus P1 over the density. We will then look at the potential energy per unit mass, which will be gravity times height 2 minus height 1. We will then look at the kinetic energy per unit mass, which will be defined by velocity 2 squared minus velocity 1 squared over 2, which would all be equal to the frictional heat per unit mass. Now, our next step is to decide what we want in our system to be 0.1 and 0.2 for our values here. We're going to define up here as 0.1 and right at this outlet here is 0.2. Now, these 2 points have the same pressure, so we can actually cancel out this whole term right here. They do have different heights, so we're going to keep this term. And then when we're looking at velocities, velocity is very dependent on the cross-sectional area of the hole or the opening. So when we look at the cross-sectional area at 0.1, it's very large. It's probably moving very slow. There's very slow velocity. And then when we look at point 2, that little hole, the water or whatever liquid it is probably shooting out pretty fast. So in comparison, we can assume that at point 1, the velocity is 0 because it's moving so slow compared to the point 2. So we can cross out this velocity 1 term right here. And then just to simplify things, we can also get rid of this q value over here and make that equal to 0. So to rearrange what we have to solve just for velocity, we have v2 equals, and then we will have the square root of g z1 minus z2, and that is multiplied by 2 as well. 2g z1 minus z2. Now to avoid this term being negative, since we are taking a square root, we can define z1 minus z2 as just this h1 value. And then we can use positive 9.81 meters per second. And then, so, we can rewrite that as the square root of 2g h1. And then so, to put our velocity into an actual flow rate, we have to multiply that by the area of this outlet hole, defined by AH. So we can say Q1 equals this term that we solved for right here times AH. So we have AH square root of 2G H1. So now we have Q1. So we can rewrite this equation up here is, and we'll also move the cross-sectional area over there out of the derivative since it is a constant value. We will say dH1 with respect to time, so the change in the liquid level in tank 1 with respect to time equals this flow rate in minus this Q1 that we just solved for, which is the cross-sectional area of the outlet hole times the square root of 2G H1. So now we have our first dynamical material balance here. Now we found Q1. Q1, the outlet of tank 1, becomes the inlet of tank 2. So when we look at tank 2, we have the change in the liquid level in tank 2 with respect to time will equal Q1 minus Q2. Now this term here, this is Q1. So we already have Q1. Now Q2 will look very similar. Q2 will equal that same cross-sectional area of the hole times the square root of 2G H2, because now we are looking at tank 2. So now we will have, I'll just write all three of them over here. We have DH1, the change in liquid level in tank 1 with respect to time, equals Qin minus the square root minus AH times the square root of 2GH1. And then we know 2, the change in liquid level of tank 2 with respect to time equals Q1 minus Q2, with this being Q1, and then our Q2 being AH square root of 2GH2. Then we can look at the change in liquid level in tank 3 with respect to time. So we know that will be the inlet of tank 3, which is the outlet of tank 2, which would be Q2. So you have Q2 minus Q3. Similarly, Q3 will be AH square root of 2GH3. So now we have our three we have our three material balances here. And now we can simulate these in Colab.
All right, so now we can go ahead and move on to the coding part of this problem. So I went ahead and copy and pasted our problem statement right here just so that we have it. I've also imported a few libraries so that we can call functions such as square rooting, solve IVP, and also plotly so that we can actually plot our solution. I've also went ahead and defined a few variables here. We know that we'll need gravity for this problem. And then I have set our area to 1 meter squared, as said in the problem statement up here. And then the drainage hole to 0.1 and our Q in naught as 1 meter squared per second. So now that we have all of this, we need to define our H naught value. And to define this, we're actually going to have to revisit the equation that we just solved for. So I will go ahead and use this whiteboard right here and write that out. So we came up with the change in height with respect to time to be equal to 1 over the area, see that, times Qn minus the drainage hole area times the square root of 2GH. Something important to note about this equation is that our variable that we are taking the derivative of, h, is being raised to the 1/2 power because it is in a square root. This means that our equation is nonlinear. And we're actually going to want to solve for h here and isolate it from the rest, rearrange the equation. So we're going to set this to 0, and when we rearrange this equation to solve for h, we're going to end up getting h, and I'm going to call it h naught, equals Qn, and I'm also going to call that Qn naught, over the drainage hole area. That term is going to be squared to undo the square rooting here. And then that's all going to be divided by 2g. So now that we have our h naught value, we can go ahead and plug that into our code. All right. So we have h naught to be equal to Qn naught divided by AH to the second power, and that will be divided by 2 times g. Great, so now we have our h naught value. We're also going to need to define our set point, which is the height we want our third tank to be at. Now from our problem statement, we know that we want the third tank to be 20% higher than the initial steady state. So we're going to say that HSP is equal to 1.2 times h naught. Now that we have those defined, we are going to jump into our proportional only controller. We're going to call this KC, and right now we're going to assign it a random value. We don't know what value will work for our system right now, so we're just going to call it this and revisit it later on. And then we are going to do our Tn to be equal to 1000. This is the amount of time that we want our simulation to run for in seconds. So now we have it at 1000 seconds. Now that we have this, we're going to define our t-plot to be equal to space 0 Tn 1000. What this is doing is basically creating 1000 evenly spaced time points for our plot. And now let's see what H naught and HSP actually are with these values. You can go ahead and press Shift Enter. And we see here that our H naught value is 5.102 and our set point is at 6.12. So the 6.12 is what we want our third tank to eventually reach. All right, so now that we have that, our next step here is to define the right-hand side of our equation. We are going to say t, our variable for time, and then vec, because we are going to have multiple heights that we are using. And then we're going to say h1, h2, and h3 are equal to vec. And now we're going to put in our q1, q2, and q3. And because all of these values are relatively similar, I'm going to go ahead up here and create another variable called alpha so that we don't have to write everything a few times. So alpha is going to be equal to the drainage hole area times the square root of 2 times g. Right? And now we can go ahead and say these are equal to alpha times the square root of h1 for q1. And then similarly, we're just going to type the same thing for q2 and q3. So alpha times the square root of h2, oops, and then alpha times the square root of h3. All right. And we're also going to want to define our error. This is going to help with our proportional only controller. So we're going to define our error as E, and this is going to be equal to our set point height minus what the actual height in the third tank is. So for example, if our set point height is at the 6.12 and the actual value of the liquid level height in tank 3 is 6.1, then it would be 6.12 minus 6.1. Our error would be very small at 0.02. So now to define our actual Qn. This is going to be equal to our Qn naught plus our proportional only controller times the error. Right? And we want to return a few things. So we are going to put return, and then we're going to return Qn minus Q1 over A. These were our material balances from earlier. And then Q1 minus Q2 over A. And then Q2 minus Q3 over A. All right. And we can go ahead and press Shift Enter there, make sure there's no errors. And now we're going to want our result to be equal to solve IVP, solve our initial value problem. That's going to be of RHS, and then we're going to say 0 to end. And then we're going to do P dot full 3H naught because they all have the same starting value there. And then we're going to want our method to be Radeau, spelled that wrong, and dense score output to equal true. Right. Going to want our H plot to be equal to res dot sol T plot, and then we're going to want H1 plot, H2 plot, and H3 plot be equal to H plot. Oops. Okay, we can go ahead and press Shift Enter there. No errors, it's good. And then we want to actually plot our solution here. So we're going to do fig equals make underscore subplots, fig dot add scatter, and then we want our x to be t plot for time, y to equal h1 plot, and then we want the method or mode. We want the mode to equal lines, and we're going to name it H1. So all of these are going to be pretty similar here, so I'm just going to go ahead and copy and paste this line and just change the H1s to H2 and H3. H2, H3, and then H2 and H3. And then we're just going to update the layout. So update layout. Let's make our width 600, height equal to 400, and then we want our template, just to make it look good, to be plotly underscore dark. Right, and then shift enter, see if we have any errors there, and looks good. So we can see we have our 3 liquid levels present on this graph here, and can see that the value right here looks to be about 5.6 for these tanks. And up here, we remember our set point is 6.12. So that's pretty far off from our set point. So let's revisit our proportional only controller up here. Let's change that value and see how this can improve our value down here. So I'm just going to put it as 1, see what happens there. All right, so we can see that they kind of diverge right here. So it doesn't seem to be a good KC value. Yeah, so let's decrease that. I'll go maybe in between at 0.5. Okay, so we have some oscillations here. That is our proportional only controller and our error actually sort of adjusting as it goes, increasing and decreasing that value to get closer and closer to our set point. And so we see that we are at 5.96 now, which is a little better than earlier. It's almost at 6, but it's still not quite at our set point. So let's try increasing this a little more, maybe 5.8. Okay, so it diverges again. That's not what we want, so maybe that's a little too high. I'll go down to 5 or 0.7. Okay, so this is a little closer to what we want to see. It's adjusting as it goes, but to really see our maximum controller value, we actually want the oscillations to kind of be all the way up here and all the way down here. Oops, what did I just do there? Okay, there we go. We actually want it to be full to see what the value of KC is right before the system becomes unstable, which is when it diverges. So we want to see how close we can get before the system becomes unstable. So let's increase it just slightly, maybe 0.75, and let's see. So we can see that is a little too big here because it's actually getting farther and farther away from where it starts right here. It's not really closing in on a certain value. It's kind of diverging more. This is definitely also too large of a value for our KC value here, because you can see it's 9.22 here, but then it goes all the way up to 12.58. So let's decrease that very slightly. We'll do 0.72. Okay, so that is definitely better. That's much closer to what we want. It's not quite full. There's still a little dip, as we can see in these values. So let's increase it a little more. It's maybe out of 5 right here, 0.725. That looks pretty good. That looks pretty full. Maybe a little dip, barely. So let's 0.727. That looks very good. The oscillations are just right at the top bottom. They look pretty consistent. This looks like it is a good proportional only controller constant right before the system collapses. Let's increase the value a little more to see if the system collapses if we increase it. And we can see it does slightly increase there. So let's go up a little more, maybe 0.73. Yeah, so we can see here that the oscillations are getting bigger. So I would say 0.727 is going to be our maximum value of this Kc variable before the system becomes unstable. Right, so thank you for watching this video.